In this video I'm going to be doing a walkthrough of the Mathematics Extension 2 exam from 2016. And this is the exam that would be taken in Sydney, for example, for those non-Australians who may have stumbled upon this video. So what I suggest you do, if you haven't attempted this exam recently, is just pause the video whenever I come to a new question, and then you can have a go and then see how I did it. Question 1. With this one, you can see that on the graph it's defined for negative x as well, not just the positive x. So that immediately rules out these two, because if x was negative in here, that wouldn't work. You can't take square root of a negative number. So it's going to be one of these two. And then, so we just need to decide whether y, or absolute value of y, is sensible. If it was absolute value of y, that would mean it wouldn't matter if y was negative or positive. So we'd expect to see sort of stuff down here as well. Because, for example, if 1, 1 would satisfy all of these, but with this one also 1, negative 1 would, because if you stick negative 1 in there, that would work as well. So it can't be that one either. So it's going to be C. Question 2. Let's start with looking at A. So we could try first just substituting that in and see if it at least has a single root. So when we sub x equals 1 into that, we get 1 minus 1 minus 1 plus 1, so that equals 0, so that's good. So it's got at least one root. To work out if it has multiple roots, we could try factorizing it. So what I might do is look at these first two terms and look for common factors. So you've got an x to the fourth in both of those. And then with this next bit, well, it's like subtracting x squared minus 1, and we know because of difference of two squares that that's x minus 1 times x plus 1. And then that's really useful because we can take the x minus 1 out. And now what we can do is plug the x equals 1 into this bit to see if it's also a root of that part. When we do that, we get 1 minus 2. So that doesn't work. So it's only a single root with that one, not a multiple root, so we can cross that out. With B, when we plug in x equals 1, we get 1 minus 1 minus 1 minus 1, which is actually minus 2. So that one doesn't even have a single root, so we can rule that one out. With C, if we plug in x equals 1, we get 0 again, so that's good. So let's see if we can factorize that a bit more. You got a common factor of x cubed with the first two, so let's take that out. And then we can take out the x squared minus 1. And now you can see if you plug x equals 1 into here, you actually get 0. So that means that it's a root of this part and of that part, so that one's good. That's actually the one with the multiple root, so it'll be C. But just to check, let's look at D as well. So again, when we sub in x equals 1, we get 1 minus 1 minus 1 plus 1, so that's 0, so that's good. There's at least a single root. Let's try factorizing it. So let's take out the x cubed from the first two. And that's x minus 1 times x plus 1. So let's take the x minus 1 out the front. And then if we try subbing in x equals 1 to this bit, you get 1 times 2 minus 1. So that's not 0, so that doesn't work. So it's only the single root for D, so definitely C. Question 3. This one's just a matter of knowing what ranges that eccentricity can take for the various conic sections. So a circle will have an eccentricity of 0. An ellipse will have an eccentricity between 0 and 1. A parabola would have an eccentricity of 1, and a hyperbola is going to have an eccentricity greater than 1. So if we want this sum of the two eccentricities to be 3 on 4, well, it can't be B, because if a parabola has an eccentricity of 1, then the sum's going to be more than 1. And same with these ones that have a hyperbola in them, because that's going to be more than 1, so that the sum can't be 3/4. So it has to be A. Question 4. Alright, so we're looking for which one of these four is going to end up in this quadrant. That's the third quadrant. Alright, let's figure out where everything is. Negative w is going to be over here. So that's in the fourth quadrant, that's not what we want. 2iz, now you might be thinking that's like rotating by 90 degrees twice, but what it actually is iz would be rotating the z by 90, so like that's 90, and then 2iz is that scaled up by 2. If we actually wanted z rotated by 90 degrees twice, it would be I squared times z, not 2iz. So anyway, that's in the second quadrant, so that's also not what we want. Z bar, conjugate of z, that's going to be the reflection of z about the x-axis. So that's going to be down there. And that's in the fourth quadrant again, so not that one. Now w minus z, I would think of that as like minus z is like this vector out here, and then you're adding that onto w, so it's like having that. So that vector there is w minus z. So that is in the third quadrant, that is what we want. So D is the answer. Question 5. I like this one because there's a couple of ways that you can do this. You could think of it as in sort of two steps, multiplying by 1 minus I and then dividing by 1 plus I. So let's think of both of those separately. So 1 minus I, if we imagine an Argand diagram, is a sort of a vector out here. So if we're multiplying by that, we're going to be rotating by this angle, so 45 degrees clockwise. And then the 1 plus I is out here with an angle of positive 45 degrees. So if we're dividing by that, though, that's going to make it the other way. So again, 45 degrees clockwise. So this first bit goes 45 degrees clockwise, the next bit also goes 45 degrees clockwise. So in total, it's 90 degrees clockwise, or pi on 2, yeah, B. So we can also do it by just working out what this number is. And you do that by multiplying the top and bottom by 1 minus I. And that's to make the bottom into a real number. So on the top, you get the 1 times the 1 is 1. 1 times minus I minus I times 1 is again minus I. And then minus I times minus I is minus 1. Because the two negatives cancel out, and then the i's together make minus 1. On the bottom, you'll find you have, okay, 1 times 1 is 1, 1 times minus I is minus I times that, and then plus 1. So those cancel out, which was the reason that we multiplied by 1 minus I in the first place. You just multiply by the complex conjugate, and that will make that into a real number. So that cancels with that. You get minus 2I over 2, or negative I. So on the Argand diagram, that's down here. So again, that's going to be a rotation of pi on 2 clockwise. Question 6. I've just pasted the relevant part from the reference sheet onto here so you can see the formula that we need. So I know a lot of people are confused about function notation, so let me just be clear first. When we do p of x plus 1, so we're plugging x plus 1 into wherever you see x there. So that's going to be 1 plus x plus 1 plus x plus 1 squared and x plus 1 cubed and so on, up to x plus 1 to the 12th. And we're interested in the coefficient of x to the 8. So we actually don't care about all these earlier ones because they're not going to give any x to the 8 terms. So they're, whatever. And we're going to have, the first one that we're interested in is the x plus 1 to the 8. And then to the 9, and 10, and 11. because those are the ones that are going to give x to the 8 coefficients. And so applying the binomial theorem, if we've got like x plus 1 to the n, that's going to be, you can use whichever one of these you want, it doesn't really matter. Now the b to the n minus k, because b is 1 in this case, that's just going to be 1 each time, so we can kind of ignore that. So each one of these is equal to this sum, and since we're only interested in the coefficient of x to the 8, we just want to look at the part of this where k is 8. So that's going to give us n choose 8 times x to the 8. If you used the other formula, you'd get like n choose n minus 8 times x to the 8, which is the same thing. So for this one, I mean, you probably know that that's just going to be 1 times x to the 8. Actually, I'll take the x to the 8 out the front. So there's just a coefficient of 1 from that. If you were like going off the formula, it would be 8 choose 8, which is 1. And then for the next one, you're going to have 9 choose 8, which is just 9. And then for this one, it's going to be 10 choose 8, or 10 choose 2 if you use that formula. And then you've got 11 choose 8 and 12 choose 8. So those are all the coefficients. We just need to add those up. We don't care about all the rest of it. So I'll just use the calculator for this. Hopefully your calculator looks something like that. And we'll have a button that says something like NCR somewhere. And that's how you do these bits. So 1 plus 9 plus 10 choose 8 plus 11 choose 8 plus 12 choose 8. And that gives us 715, so that would be C. Question 7. You might have memorized how to do this kind of question, but let me just go through why it works for those of you that don't know. So this would be the graph of xy equals 8, and then the x squared minus y squared equals k is going to look like this. So it's just this one being rotated. Now what we want, if they're the same hyperbola, is that this distance there has to be the same as that distance. So we can work out that distance because we know the equation of this. So this would be the point where x equals y, because it's on that line. And if xy equals 8, that means we need root 8 are the coordinates of that point. So we can just use Pythagoras' theorem to work out that distance. So that squared plus that squared is 16, so this is root 16, which is 4. So we want this distance to be 4. So that is going to be the point 4, 0. So if we plug that into the equation, the x is 4 and y is 0, we'll get that k is 16. So D. Question 8. You can see with the possible answers to this one that the question is just about whether there should be negatives or positives here. So the question is really about the horizontal and vertical components of these forces and what directions they're going in, like are they pushing in the same direction or in opposite directions. So if that's theta, and that's f, then this is going to be f cos theta, and that's f sine theta. With a little bit of geometry, you can see that that angle is the same as that one. So that's also theta. So that's going to be n sine theta there, and n cos theta. So let's think about if we want f cos theta plus n sine theta, or should it be minus? Well, the f cos theta is in that direction, sort of inwards, whereas the n sine theta is going outwards. So they're working against each other. So that should be a minus, because we want that one minus that one. That gives the total force. So that rules out A and B. And then with the vertical components, you can actually see they're both pushing upwards, so they should be added. So the f sine theta plus n cos theta, so that's C. Question 9. This one's just a matter of expressing the length and width of that rectangle in terms of h. So if we think of it as how far up we are as being h over 4, like on a scale of 0 to 1, with 1 being up here and 0 being down there, then h over 4 is how far up we are. And then the width has to start at 2 and go up to 8. So it needs to be 2 when h is, well, when this is 0, and 8 when this is 1. So the way you would do that is that it's 2 plus, and then it needs to go up 6 to go to there, so 6 times our little factor. And similarly for this, it needs to go up by 4 to go from 3 to 7, so 3 plus 4 times that factor. So you can just, to make sure, you plug in h equals 0 and you get 2, so that's good. And plug in h equals 4 and you get 8, so that works, and the same thing for that. And then you just need to simplify these, so that's 3 plus h, and that's 2 plus 3h on 2, or 3h on 2 plus 2, so that's that, and that's that, so A is the correct answer. Question 10. This one I'm going to have a bit of fun with because there's a couple ways you can do it and you don't actually have to use complex numbers, but I'll go over that weird and wonderful way later. Let me first just do the sort of the standard way using complex numbers. So we've got this equation. We can turn that into a quadratic equation by multiplying both sides by x. So you get x squared plus 1 equals negative x. Shift that across, and then we've got a standard quadratic equation that we can solve using the quadratic formula. So negative b, where b is 1, plus or minus square root b squared minus 4ac is going to be negative 3. And then all over 2a, which is 2. And so that's going to give us negative 1 plus or minus root 3 times I over 2. And just to get an idea of where that is, it's sort of out here, where, well, it wasn't drawn very well, but that's a half, and that's root 3 on 2. So we can work out the modulus and argument of that. So that length, just using Pythagoras, is going to be square root of root 3 on 2 squared plus half squared. So that becomes 3 on 4 and 1 on 4. And you add those together, you get 1. So that's just going to be 1. And for the angle, you've got like root 3 on 1 there. So arctan of that is pi on 3, or 60 degrees. So that's 2 pi on 3. And so it could also be negative, it could also be down here instead. It doesn't really matter which one, they're both going to have the same answer, so I might just ignore the negative solution. So to work out x to the 2016, that's going to be 1 to the 2016, and then the angle is going to be 2 pi on 3 times 2016. Now, because 2016 is divisible by 3, like you can see that the digits add up to 9, so that's divisible by 3. So the argument of x to the 2016 is going to be a multiple of 2 pi. So essentially, it's just on the real axis, and is 1. So x to the 2016 is just 1. We've got 1 plus 1 on 1, so 2. So b. Now, the other way that you could do it, probably not the quickest way, but you know, it's a bit of fun. So we've got this equation. I'm going to square both sides. You would sort of get the idea to do this by, I mean, like, your instinct might be, if you weren't great at algebra, would be to raise both sides to the power 2016. And of course, the younger students will forget that there are all sorts of cross terms in there. But you know, maybe we try squaring both sides, because then the cross term is going to be quite nicely behaved, because you're going to have the x times the 1 on x. So you've got 2 times x times the 1 on x, so it's 1, so just 2. And plus that. And negative 1 squared is 1. So let's shift that across. So we get -1. Okay, that's interesting. Now let's see what happens if we multiply this equation by this one. So that times that, we're going to get x cubed, and then you've got the 1 on x times the x squared, that's x, and the x times the 1 on x squared, and then that times that. And then on the right you've got that times that, so 1. Now we know what that is, because that was in the original equation. That's -1. And then let's move that over the other side. Alright, great. Well, we can keep doing this. We can multiply that by that again. 4 plus... And we worked that out up there. That's -1, so let's move that across. So by now you might be suspecting a sort of a pattern. We had -1, and then -1, and then 2, and then we're getting -1 again. And you can see from what happens that, you know, when we get to the power 3, we've got power 1 there. When we got to 4, we got power 2 in there. So each one is going to just depend on the previous one and the one before that. So like the x to the 4th plus 1 on x to the 4th depends on what x cubed plus 1 on x cubed was, and also what x squared plus 1 on x squared was. So if we continue this, it's just going to be like -1 and then 2 and then -1 and so on, where every third one is a 2. And so because 2016 is divisible by 3, it's just going to be 2, the same as x cubed was, and the same as this will be the x to the 6th plus 1 on x to the 6th will be 2, and so on. So B. Probably not an easier method than the first way using complex numbers, but it's interesting anyway.